Okay, in the last video, we solved exponential equations using logs. We use log base 10, but today we're going to talk about how to solve using logs with different bases, and we're going to use the idea of inverse functions. So we have to remind ourselves a little bit about inverse functions. So let's think for a few minutes about the things that we know about inverse functions. We talked a lot about inverse functions. We know lots of things about them. We know that their graphs are, they reflect over that line y is equal to x. We know that to get an inverse function, you switch the x and the y's and you solve for y. We know that the input of a function is the output of its inverse function. But the one that we're most interested in today, the property that we need to talk about most, is this one that I have written down here. So let's remind ourselves what this cuckoo notation means. F is a function. That means his name is f. So if I have a function f of x and I have a function f of f negative 1 of x, this is function whose name is f. This is his inverse. So function f, inverse of function f. And these are just names. It looks like a funny notation. This all means the y value of my function f. This means the y value of my function f. So the function value of my function, the function value of my inverse function. All right. And this weird notation, if you remember, talks about combining functions. So this one says, if I take f and compose him with his inverse, and they both have x as the variable, you're going to have an output of x. So this notation actually means this thing. It says take function f, and everywhere you see x, you're going to stick the inverse inside for x. And you should get out the same thing that you started with. So this is that idea that we talked about in class where, if I hand you a $20 bill, I hand everybody a $20 bill as they walk into the door, and then Mr. McManus shows up and he starts taking $20 bills from everyone as they walk out the door. What's going to happen is you're going to end up with whatever you walked in with. So not everybody's going to walk out with the same thing, but you're all going to walk out with whatever you started with. And this is the idea of composing functions. I'm a plus 20. Mr. McManus is a minus 20. We're inverse functions. We're doing the opposites of each other. So when we do them consecutively or right in a row or right together, you actually end up being the same as you were before we started. Okay, so let's take a look at this with a set of inverse functions that we can know a little easier than our logs and our exponential functions, because I think it'll help our brain to understand a little better. So here's my function, and this is the one that does the opposite. So this subtracts a 1 and multiplies by 3. This, adds 1 and divides by 3. So these guys are going to be inverses of each other. And how do I know if they actually are inverses? Well, I'm going to use this idea. If this is true, if f comes out to be x, and the other thing, this one, when I do them the other way, when I put the function inside the inverse, if it comes out to be an x, then we know that we have inverse functions. So you ready? How are we going to do that? Well, I'm going to take my function f, and everywhere I see x, I'm going to put a parentheses. Because this tells me, so let's pretend we're setting it equal to this now, right? So this tells me that put whatever the inverse function is. And what's the value of the inverse function? This little expression right here. So that's what I'm going to put inside. So from here, you can see these 3's cancel. I get x plus 1 minus 1. X plus 1 minus 1 is x. So we know that it works for this one. This did come out to be x. We got back what we started with. We know that so far so good. It looks like these actually are inverse functions. Let's do it the other way. So if I have f, the inverse, and I put the function inside, that's going to give me, well, I take my function, my inverse function, and everywhere I see x, I put a parentheses, and what am I going to put inside there? Whatever my function is. So that one is 3x minus 1. Okay, so 3x minus 1 plus 1 is obviously 3x over 3. Our 3's are going to cancel, and we get x. So this is how you show, if anybody ever asks you, prove that these are inverse functions. This is what you do. You take each one and you put them inside the other and see if it comes out to be an x. And if they do, then they're inverse functions. Now, why in the world is this important to us? Well, the reason why this is important is because if you remember, logs are the inverse to exponential functions. And if you remember, we said that is exactly the whole reason logarithm functions exist, is so that we can undo exponential functions so that we have an inverse function. Okay, so let's take a look at this one. Let's say that y is e to the x, and this one is y is log base e to the x. Okay, so my base here is an e. You can use whatever base you want. It doesn't really matter. Makes no difference. But what does this little expression say? This says the exponent that you need to raise e to get x. That's what he says, right? So y is this exponent that I have to raise e to get x. To get x. So this one says that when I raise e to the x, I get a y. All right, so take a look. This x is the exponent. And in this one, y is the exponent. Do you see how they've switched places? The input of this one is the output of this one. The exponent and the exponent have switched places in the expression, right? The input, it was the input here, it's the output here. And over here, x is the value after you raise it to the power, and in this case, y is that value. So x and y have switched places. The input and the output have switched places. These guys are inverse functions, okay? And what happens when we compose inverse functions? So let's call this one f of x, and let's call this one f inverse of f of x, okay? So we'll call them that way so that we can talk about them. Or, I don't know, maybe it's easier just call this g of x. Maybe that'll even be easier. We'll call him g of x so that when I'm talking about them, you'll know what I'm saying. All right, so the first thing I'm going to do is I am going to, let's do this one first because I think this one's a little bit easier to see. Let's take these two functions and compose them. So I'm going to take g and I'm going to put f of x inside of it. So what is g? It's this guy. It says log e, and everywhere I see x, I'm going to put a parenthesis. And what am I going to put inside there? I'm going to put inside this guy. So I'm going to put inside e to the x. Everyone with me? So I took this function, and everywhere I saw x, I put this function inside. I put f inside. All right. So now what does this expression say? We have log base e to the x. Well, if you're having a hard time with these letters, just think about it as log base 2 of 2 to the x. This is kind of saying the same thing. This says, what do I have to raise 2 to get 2 to the x? Is there anybody that doesn't know what that is? What do I have to raise 2 to get 2 to the x? What do I have to raise e to get e to the x? Hopefully, everybody sees that that is a big fat x. Does everyone agree with that? See how when I compose them, I got the x back out? All right. Now the other one's a little bit more tricky to see. This one goes like this. It's f of g of x. And this one says e to the something. And what am I going to put in there? I'm going to put log base e of x. Okay. All right. So this says if I take e and raise it to the log e to the x, what will I get out? Well, take a minute to remember what this little expression means. What do we say that this one is? If I were to describe it in words, it says the number you need to raise e to to get x, right? That's what we just said it was up here. I'm the exponent that you need to raise e to get x. I'm the exponent that you need to raise e to get x. So if I'm the number that I have to raise e to get x, and I'm raising e to that number, well, what number would that give me? That's going to give me an x. Okay, so if you're having a hard time seeing it, once again with this, let's do it with something a little bit maybe easier to see. Let's take y is equal to 2 to the x, and y is equal to log base 2 to the x, okay? So we'll make this one h of x and this one k of x. So if I take h and plug k inside, so compose them, I get 2 to the x, not 2 to the x because I'm going to put k inside, 2 to the log base 2 of x. Okay. So this says whatever I have to raise 2 to get x, that's what I am. And I'm raising 2 to it. Okay? Again, still having a hard time. The reason why I picked this one is because we're going to do it with a number. You ready? Let's this time say log base 2, oh sorry, I thought you could see it. Log base 2 of 4. What's log base 2 of 4? This is whatever I have to raise 2 to get a 4. That's a 2. This one, log base 2 of 8. What do you have to raise 2 to get 8? 3. One more. Log base 2 of a half. What do I have to raise 2 to get a half? -1. Okay? So if I said this, 2 to the log base 2 of 4. What's this expression equal to? It's whatever I have to raise 2 to get 4, right? So what number is that? Or in other words, we could write 4 as 2 squared. So that's almost like saying log base 2 of 2 squared, right? And this one is 2 to the third, and this is 2 to the -1. All right, so look at this one. If I say 2 to the log base 2 of 8, this says whatever you would raise 2 to, I'm sorry, this is not a 2, it's a 4. What am I talking about? Because this is a 2. I almost lost my mind, right? 2 to the second is 4. So do you see how we got back what we started with? 4 was the input here. We got 4 out. Take a look at this one. Log base 2 of 8. This says whatever you have to raise 2 to get an 8, that's the number I am. It doesn't even matter what it is. We happen to know it's a 3. But it doesn't matter. It's just saying that I know I'm using whatever number I have to do to get an 8. And so this one comes out to be an 8. And if I do 2 to the log base 2 of a half, it says whatever number you have to raise 2 to get a half. So what must I be when I raise 2 to me? I'm going to be a half. Because we know that this thing is equal to -1. And it doesn't even matter if we knew what it was equal to. Because if I had 2 to the log base 2 of 7, which I have no idea what number that is, but I do know that if I raise 2 to it, I'll get a 7. So that means that this has to come out to be 7. This is this idea of this inverse function. I'm getting out whatever my original input was, because these are inverse functions. Okay? All right. Now, all of that so that we could look at our example and use this idea to actually solve an equation. Okay? So, if I have, we'll use the equation that we had in the other example. And I made it super humongous for some reason, but here it is. Let's say it's this one, 11 to the x minus 13 plus 5. Now, in the last episode, we used log base 10 to solve this one. But in this case, I'm going to use actually log base 11. And why am I going to use log base 11? Because these two are inverse functions. Log base 11 and 11 to the something are inverse functions. Oh, and I don't want to do that first. Oh, silly. Sometimes I think I lost my mind. Let's pretend I subtracted 5 first and didn't lose my mind, right? That's what we should have done first. And then over here we had a 62. So hopefully I didn't just lose you. So once again, I log both sides, but this time I used log base 11. And I used log base 11 because the base of the exponent that we were solving for here is 11. If it were a 7, I would have used log base 7. If it were 10, I would have used log base 10. But in this case, I'm using an 11. Okay, so we subtracted the 5 from both sides to get the 11 expression all by itself. And then I log both sides just like I did in the last video. So these two things are now equal. Over here, this says on the exponent you got to raise 11 to get x to the 13th or whatever, or when I compose these two, right? This is like this idea here. Let me see if we can find it real quickly. It's like this one right here, right? When I compose these two inverse functions, well, I know that what do I have to raise 11 to get 11 to the x minus 3, x minus 13? Obviously, it's x minus 13 on this side. And this one is log base 11 of 62. And now the last thing that I have to do is add 13. I'm going to put this in parentheses just so it doesn't look too confusing. Because I know sometimes people get confused if there's no parentheses. They don't know if the 13 is inside or not. If there are no parentheses, the 13 is not inside. It's the closest. But all right, now that number, it's hard to know what that is. And if you were watching the last video, you know that I actually don't have a calculator that you can put base 11 into. I only have a calculator that you can put base 10 into. So we're going to go over one more new thing. Are you ready? Okay. Put your thinking cap back on for one moment. We're going to do change of base formula. And what this change of base formula is going to do for me, it's going to take a log that has some base, it doesn't matter what base it is, and it's going to convert it to whatever base I want to change it to. So if I rewrite it like this, I can get the same value with a different base. Okay? So that means that if I have log base 11 of 62, and I want to write it in some way that I'll be able to plug it into my calculator, I want to change it to base 10 or natural log. So if I change it to log base 10, or I don't even need to write the 10 because it's base 10, and I put the 62 here, and then I do log base 10, and I put the 11 here, this has the same value as this. And this is one I can plug into my calculator. Okay? So if you remember, when we solved it in the last video, we actually ended up, this expression we wrote as log 62 over log 11. That's what it looked like when we solved it. If you go back to your notes, you can actually see that that's what it was before we changed it. And now this is something I can plug into my calculator. And so I just plug this into my calculator and add 13. I can change it also to the natural log, so I'll show you the natural log. So the natural log we write this way. This one is actually base E, and I'll show you that one on your calculator too. And then later on, if you want to look at some videos on base E or the natural log, you can do that. But just so that we can see that these two things are the same, I'm going to plug this into my calculator and this into my calculator. And they both should come out to be approximately 14.721 or something, if I remember correctly from the last one. All right, let's take a look. So the first one is just log. So I'm going to do log. So I'm going to do 62 divided by log, 11. Enter, and then I'm going to add 13 to it because that's what this says, add 13 to that. So it's this expression plus 13. So I got a 14.7211, which is actually what I got in the last video. Now we're going to use this natural log one, and if you look on here, there's one that says ln. It's the same thing as log, except it has a different base. It's actually base E, and E is a funny number, which again, you can hear about in another video. When I divide those, I actually get the same exact number as when I divided with log base 10. Now, if you have a calculator that will do other bases, you could use whatever base you want and it would come out the same. But if you had a calculator that did other bases, you could just plug this in and you should get that same number, 1.72. So if you have a calculator that does the change of base for you, you probably don't really even need to know that much. But if you have a calculator like me that does not, which a lot of you probably do, then you need to be able to change them if you want to get the decimal approximation. But once again, if it were me, this is the answer I would probably want you to leave because I love this one. This is an exact answer. And if I convert it to decimal form, which we said was 17.211, that's just an approximation. So if they ask for an exact answer, they want you to leave the answer in terms of log anyway. Okay? I know that was a lot. Hopefully you were able to follow along or go back and look at anything that seemed confusing.